Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. The topic will be adversarial search and games. This is chapter 6 from the book. So let's begin. Adversarial games. So just a brief intro. In real life, there are many competitive environments in which there are two or more agents competing against each other. Sports, markets, combat, etc. Here we'll discuss simple two-player games like chess, where the actions and rules are well defined. These are suitable for AI education and research and speaking on the algorithms that can work in such competitive environments. Games can be deterministic or stochastic. In stochastic games, we mean that there's an element of randomness involved in the game, like dice throwing or shuffling of cards. Perfect information or imperfect information. So that means the environment is fully observable versus partial observability. Zero sum or not. Zero sum games in a two-player setting. What this means is that if one agent gains, means he gains points, then the other agent must lose an equal amount. So the sum of all player rewards is going to be zero. So this is if the game is zero sum. Here's some just simple examples of different games depending on whether or not they have perfect information, determinism, stochastic, and perfect information. So chess, checkers, and Go, these are examples of games that have perfect information. The environment is fully observable. Like chess, for example, you can see the full board. You can see your opponent's pieces and your own pieces. And it is deterministic, right? Actions taken, you know the outcomes of the actions, right? If the action is to move a piece to another location, you know that where that location is going to be, right? You don't know what action the agent or your opponent will do, but what I mean is that you do know if he takes a particular action, you do know, what the board is going to look like, right? So that's deterministic. Stochastic and perfect information. An example of this, these are backgammon and Monopoly. Maybe most of you are familiar with Monopoly, but these are environments where you can see the board completely. You can see the information of your opponents, and the stochasticness or the randomness comes because it uses dice, right? اللي هو النرد. It uses these dice throws, and that's the randomness involved. There's also games that are imperfect and deterministic, like, for example, you could play blind tic-tac-toe, or you can play blind chess where you don't see some of the pieces of your opponent. There's another game called Battleship, right? So these are deterministic games. It's just that you don't see parts of your opponent or maybe even your particular items as well. And then it could also be stochastic and partially observable, like Bridge and Scrabble, where there is maybe some element of randomness injected as well. So what we've seen so far in this course is we looked at different searching algorithms. These are not adversarial. We're assuming there's a single agent operating in an environment. The solution is a path to the goal, or when we talked about local search, the solution was just finding a goal state configuration. We want to look at optimal solutions. We used evaluation functions, heuristics, fitness function, etc. And there's many applications that we looked at. In games here, we are in an adversarial environment. It involves multiple agents operating against each other. The solution is a strategy, actually, or what we call a policy that specifies a move for every possible adversarial reply. So you want to develop a strategy for your agent to operate against his opponent. It may have time limits, cannot search for optimal actions if there are time limits. Instead, in this case, we'll find approximately optimal action. So we try to do our best given the time. There are evaluation functions also involved. We can evaluate how good a game state is for an agent to achieve and win. And there's many applications in the real world in terms of multi-agent environments. But for the purpose of teaching and education in this course, we'll look at these popular games like chess, checkers, etc. So some assumptions we're going to make to simplify the teaching is the following. As a start, we will discuss games with the following assumptions. We're only going to look at two agents for our games, and when the agents operate, these two agents operate in the game, they're going to take actions that alternate. This is called turn taking. An action taken by an agent is also called a ply or a turn. So, whose turn is it or whose ply is it? They both mean the same thing. So when we say a four ply or a four turn game, that means that four actions were taken. One by agent A, and then one by agent B, and then A, and then B, and so on. Right. So these are four turns. If it was five turns, then A. If it was six turns, then B, and so on. Deterministic and fully observable. So for now, we'll look at deterministic and fully observable. At the end of this topic, we'll look at stochastic and fully observable. And this is an important consideration. This means we can simulate the game's states computational. Because you know that the environment is deterministic and it is fully observable, you can perform some computational simulation of the logic of the game. And this will help us when we look at a particular algorithm at the end of this topic. Finally, zero-sum games. The utility or reward values for each agent are the opposite of each other. So the sum of all utility of all the players involved in the game has to sum to 1. All right. So if you look at all the players in the game and you sum their rewards, they have to sum to 1. So there has to be winners, and the losers will lose an equal amount. Even though we make these simplifying assumptions, the techniques we apply here, you can generalize it to stochastic games. You'll lose some guarantees of some of these algorithms, especially optimality. However, you can still modify the algorithms so that it can probably do well in some of these complex environments. So this is the game tree for tic-tac-toe. Most of you know tic-tac-toe. You're given a 3 by 3 board, and you are playing against an opponent, and you need to one takes turn to put an X, and another takes turn to put an O, and the winner is whoever can take a line of 3 of the same letter, X or O, right? So this is the full game tree. And what we mean by the full game tree is that imagine if there are two players playing this game. One is going to be our agent that we want to design its algorithm. We'll call it Max. And his opponent will call it Min. And we'll see why we gave it these names. The root node, let's say that you just started the game, right? You want Max to select the best action from the current state. The board is empty. So if we try to look at the full set of game states and our full possible actions, we can generate a game tree. The root node will be the empty board, which is the initial state of the game. And the branches that you see here are the actions that Max can take from this state at this node here. So we'll call this the game node or the game tree node, right? So these are all nodes, right? And they contain game states, okay? So at this level, at the first root, the branches that you see here are the actions available for Max. So Max can take an action like this left branch where he puts an X in this position, or he can take an action where he puts an X in this position, and so on, right? There are 9 possible actions at this game state here, right? Now, at another particular game state at a lower level, like here, in this game state, it is actually the turn of the opponent, which we'll call Min. And he will also have branches that are the actions that he can take, right? And the actions he can take is where can he place the O? He has 8 possible ways he can place the O. And then at this game state here, or the node here, it will be Max's turn. So you can see that the game tree here encapsulates from the root state, whichever is the root state, right? The entire set of possible actions and the turns that can be taken until an end game state is reached. So you can see at the bottom of the tree, which is the leaves, it contains end game states. And at end game states here, these are still game states. It's just that they're end game. We'll call them terminal states. We can calculate a utility or reward. We'll talk more about this later. But for example, because our agent is Max, the one who's we're writing the algorithms for, we'll look at the utility from his perspective. So you can see here that whoever is the O player wins, which is Min, our opponent. So we're going to give him a negative utility for Max. This is a tie state, so we give him a 0, and this is a win state, so we give him a +1, and so on. So the idea is that I just wanted to show you the game tree in its entirety for the game of tic-tac-toe and the levels that are involved. The levels are the turns, and max is the agent we want to design, and min is our opponent. And each level is a turn taken by max, then min, then max, then min, then max, until a terminal state is reached. Okay? And one important consideration is that the game tree will be maintained in some format or used by, I would say, used by the agent that we design in order to, search for a path down this tree and then determine what action should it take from this current state at the root based off of the path or the search that it done in this game tree. And we'll talk a little bit about this, inshallah. So formally, what I want to say from the example I've shown is that we can define a game as follows. S0 is the initial state of the game or the state at the root node. Okay. To move S, if you wanted to code this up, we're looking at a deterministic and fully observable game. So to move, it just specifies the player whose turn it is to move in the state S. Actions of S, it specifies the actions or moves that are allowed in the game state S. Result of SA, the state transition model that specifies the state resulting from applying an action game in the state S. Is terminal S, this is true or false, specifying if the game has ended. So for a given game, these need to be carefully defined for your given game. And then finally, there's the utility of S and P. This is a utility function that specifies a numeric value given to the player P in terminal state S. For example, in chess, we can award a +1 for the winner, a -1 for the loser, and a 0 for the draw. In backgammon, it can range from 0 to 192. So given the current state of the game in the real world, what's going to happen is that most of our algorithms is going to operate as follows. So imagine you're in a current state of the game in the real world. In the real world, right? This is the current state. What Max is going to do, our agent, is that he will use maybe some computer vision or sensors to look at the game in the real world, and then he will model a state representation of this current state in the real world. Then what he'll do is that he will start the root node and put the current state, the current game state, and then he will computationally search the game tree using, these defined functions that he has somewhere in the code, right? How does he know, for example, from this current state, what actions are available? He can call this function so that he can then do the branches. How does he know that if he applies this particular action, what this state at this node is going to be? He calls result. And then how does he know if a state is a terminal node? He can call this function and so on. So Max will computational search a game tree to select the best move at the root. Think of Max as the agent we are designing. So for tic-tac-toe, again, this is the full game tree starting where the empty board. In tic-tac-toe, there are a total of 9 factorial terminal nodes. So this is easy to search through fully because this is not a lot of nodes in terms of size. However, for chess, there's actually over 10 to the power of 40. So in chess, you cannot fully realize the full game tree without paying a lot of cost. So the takeaway is we cannot realize the full game tree for most games or most complex game environments. So what can we do in terms of the algorithms that will allow us to start from a current game state as the root node and select, remember, the goal is from the current game state, select which of these actions are the best. That's our actual goal, right? How we're going to achieve this, we can search the full game tree, we can do maybe some tricks, but the idea is that the goal is from a current state at the root node, which of the actions I should take? Like, what is the best action to take? So what Max can do is the following. Max can computationally search a game tree to select the next move. He can apply something called the minimax algorithm. Max searches the entire game tree, then selects the optimal action at the root node. So he will exhaust the full game tree. Okay. Some optimizations that can be done to speed up this search. There's a modification called alpha beta pruning. max can maintain some extra variables and avoid searching up to half of the tree while still selecting optimal action. This is important. I highlighted in red. This algorithm, it will search the entire tree, so you will pay the cost, but you will select the optimal action at the root. This is a modification of this algorithm. You will pay some cost to maintain extra variables at each node in the game tree, but it can potentially search or remove up to half of the tree while still maintaining selecting an optimal action. So that's a good guarantee. We can also use heuristics. Max can use techniques to speed up action selection, like using a heuristic evaluation function to judge how good a game state is. With this, Max does not have to realize the full tree to make a decision. However, what it means is that we can say, I'm only going to search the game tree up to, let's say, depth 2. And at depth 2, this is not a terminal node, so I don't know its utility. But what I can do is I can define a heuristic function that will evaluate how good the states are at level 2, right? And then I will treat the heuristic value of these states as if it was the utility values, right? They're estimates. They're estimating how good each state is for the max player. And so it's not guaranteed to be good estimates and not guaranteed to select the optimal action. Finally, the last algorithm we'll talk about is something called simulation or Monte Carlo methods. Max can simulate the game from a node in the game tree, then gather statistics of win or loss ratios from the simulation. Right, so we're going to use statistics and simulations. And this will select the action that gives the good, win rates or statistics. Again, because these are estimates, it's not guaranteed to be optimal. However, it converges to optimality as you do more simulations because you have more accurate statistics. So we'll talk about each of these in depth. If it doesn't make any sense to you, that's fine. We'll cover, each of them in order. We'll start here, then move on here, then finally this. Okay, so let's start. We'll look at optimal decision-making games using the minimax algorithm. So for most games, we've already said that Max cannot hope to realize the full game tree, mainly because it's so massive. But for now, let us assume that Max can realize it and search the full game tree. If Max can realize and search the full game tree, what algorithm can be used to make optimal actions? First, we should ask how Max and Min will play. Like how will the decision making be done by both of these players? Well, a reasonable assumption we can make is that both will play optimally. They both want to maximize their reward when they play the game. This is a reasonable assumption, and it turns out this is the optimal way to design the algorithm, to make the assumption that both will play optimally. Minimax search, this is the algorithm. It will choose the action at the root that gives a game state with the highest true utility value. So what does this look like? So if we looked back at the game of tic-tac-toe, Max is the agent we are designing. Okay, we want to design an agent that maximizes its own utility. Min is the opponent. The assumption is that both players will play optimally. The game tree terminal nodes are showing the utility from Max's perspective. So the utilities that you see here, like for example, for this state is a -1 because it's actually a loss for Max. The utility here is 0 because it's a draw, and the utility here is +1 because it's actually a win for the Max player. And I want to emphasize that the game tree here that is being searched is searched by the agent you are designing. So this search is happening by the Max player because you coded up in the Max player's computer. And he's trying to say, I'm in the current state in the real world. How do I select which action is the best? He's going to use searching through the game tree and then inspect terminal states. And then based off of the utilities that he sees here, he's going to use the minimax algorithm. Since it's a zero-sum game, a negative utility for Max indicates a positive utility for Min. So what I want to say, what this says is the following, this zero-sum idea. The utility here is from Max's perspective. So if this is a negative, terminal state, it's a negative value. Because it's a loss for Max, that means this is a win for the Min player because it's a zero-sum game. Similarly, because this is a win for Max, it's a loss for the Min player. So Min is trying to minimize Max's utility using this notation in this game tree, which means it will increase its own utility. So this is just notation or format used in the book. We'll use it. Okay. So what I want to say is that using this notation, when we look at the game tree, max is trying to maximize its utilities, and min is trying to minimize the utilities in this game tree because these utilities represent the utility of max, right? That's where the naming comes from. So minimax search, it wants to move to the state with the highest utility. Below is the game tree for just a very simple game that has 2 turns. And what I mean by this is that at level 0, max will take a turn. And then at level 1, min will take a turn. And then that's it. At the third level, or sorry, at level 2, the game ends. So if you look at this game tree, right, you have the utilities here from max's perspective. Okay. What is the best action that min should take? So imagine that, Max was at this state. He took action A1, and now the game is here. Now min has 3 possible actions, B1, B2, B3. If he takes B1, the utility will be 3 for Max. If he takes B2, the utility will be 12 for Max. And if he takes B3, the utility will be 8 for Max. If min is trying to play optimally, he will minimize the utility for Max. So he will select B1. Okay. And this is why we are using the max and min naming. Another thing is that we'll use the following notation for the game tree nodes. An upward triangle indicates max node, and a downward triangle indicates a min node. Okay, so if we go down this path in the search tree, and we're at this state, how did the 3 come about? So the algorithm of minimax, which I'll show now, works in a depth-first search manner because we want to utilize the storage, the linear storage that we get with tree-like depth-first search. The way it works is as follows. Starting from the current train node, from the current root node, this is the current state A. This entire game tree has not been realized yet in memory. Okay, and so from the current game state here, what happens is that Max will go down the path of A1, and then he'll generate this node here with this state. Then he'll go down the path of B1, and he'll generate the terminal node, and he sees that the cost is 3. Because the cost is 3, it will return the value to the parent node, and we'll say the current best, the current minimal action is down the left branch B1. The value of it is 3. So we have a 3. Then it will explore this path and finds that it's a 12. So performing action B2 and performing a 12 is not preferred because, this will give a higher utility for Max. So then, it says, it'll return a 2, but the minimum between 3 and 12 will be 3. Then it searches down this path and it finds an 8. And so it will return an 8 and say the min between 3 and 8 is a 3. So after searching this entire, subtree here, it determines that the optimal action for min is going to be B1, and the value at this subtree, if Max takes A1 as an action, he knows that min is going to take B1 as an action because both players are assumed to play optimally, and so Max now knows if he takes A1, the best utility he can achieve is 3. Okay. What about if he goes down A2? If he goes down the path of A2, he still needs to explore each of the other paths because maybe if he takes an action A2, he'll get a better utility. Same for A3. So if he goes down A2, he knows that min will try to play optimally from here, go down this branch. And I want to emphasize that this is all happening by in the computer of Max. He's trying to simulate this game in the computer. He finds a 2. The 2 is returned here. C2 and C3. So he knows that at this node here, min will select action C1. Okay. And then finally, he'll check this path down here. And he knows that, based off of these 3 actions, min will select D3 to return 2. Now, at this point, he has searched the entire game tree. Max has searched the entire game tree, and he wants to determine which actions at the root he should take that maximizes its own utility. Looking at the 3 actions, it is clear to Max that he should take action A1 from the root. And this is how minimax works. This is a small tree, but for a large tree, he would search the entire tree and then, propagate the values of those from the terminal states, the values of the moves from the terminal states upwards all the way up to the root. And the way it will use the searching is using tree-like DFS. So he will get the space savings cost. So the minimax algorithm that we'll write, I'll show the pseudocode, but the implementation that we're going to use is recursive implementation. It is kind of doing a return, a tree like DFS. So the minimax algorithm from a current state is it has three cases from a current state. Is the state a terminal state? If it is, then just return the utility for max's perspective. If the state or the level of this node is a max level, that means it is max's turn, then you just need to loop on the actions available to max and just recall the minimax with the transition, right? So this is kind of saying that if you're at a max node and this is the state here, then just, generate the children. And at each node here, you are going to call minimax again for the state here at the child. Similarly, if the level is a min, then it's the same idea, right? And you are trying as a max node, when you generate the children, you're selecting the maximum utility among the children. When it's a min node, you're selecting the minimum. So it's a recursive algorithm. This is it. You can take some time to pause the video and inspect it. The searching, right, starts from the root node up here. You have a game, just so you know the game logic. You need the game logic to be coded because you need to use the game logic to know whose turn it is to move. You need to use the game logic to know what actions are available from a state. You need to have the game logic to know, what is a terminal state? Is this terminal? What is the utility? What is the result function? And so on. And the state here is the current state in the real world. Remember, from the real world, Max may use computer vision or any sensor to model the current state in the computer. And the root node he will set up will be the current state of the real world. So from the current state of the real world, he will set up the Max node. Right. So at the first level, it is Max's turn. And this is the current state. And the root node will be a Max node. And this is the max node. The max node is written as a function, right? And the first check is this a terminal state? If it's not a terminal state, loop on the actions of the max node. And this is just looping on the children, right? So it's generating actions one by one. This is a max node. This is action one. And here it is calling a min node because when you perform action one, you'll generate the min node. And this is the min node code here. And when you're at this level and you generate actions for min nodes, you're going to call the max node. So this is, for example, some action at the min node B1, you're going to generate the max node, and so on until you hit a terminal state and you back propagate. And of course, you will look at other children and so on. So the code is very simple. This is the code for the max nodes. This is the code for the min nodes, and it's written in a recursive manner to search the full game tree. And you can see the returns here. This is the return from a max node. This is the return from a min node, and this is the return at this level here. You take the max value at the root node, and you return the move that you should take. Very simple algorithm. So in terms of guarantees, optimality, we made an assumption that min plays optimally as well, right? So both players are playing optimally. What happens if min plays suboptimally? The interesting part is that with this assumption that we make when we coded our algorithm, if min tries to play suboptimally, then actually max will achieve utility at least as good as when min plays optimally. For those who don't understand what this means is that max may achieve better performance if min plays suboptimally. So that means if you take minimax algorithm with the assumption, you apply minimax algorithm in your game with the assumption that min is also going to play optimally, and you run minimax and then you choose actions based off of this assumption. But then in the real world, min decides to play suboptimally. Actually, your minimax algorithm is going to perform either as good as if min played optimally or even better. So min is only going to hurt himself if he plays suboptimally. So in terms of complexity, minimax is similar to tree-like DFS. Let's say that the game ends in at most D turns and the branching factor is at most OB. Then the time complexity, meaning what is the size of your search tree, because we're generating branching factor of B at each level, right? And there are D levels, right? The game at most ends at D. Then the time complexity, which is the size of the full game tree. In the worst case, I have to search the full game tree. This is OB to the power of D. So it's exponential time complexity. But because we're using tree-like DFS, the space complexity is not actually OBD because we're not generating all the children at once. With this recursive implementation, we're actually generating a single path in memory at most. So it's going to be OD because we're not generating all the children at each node. Is it complete? Yes. If the game tree is finite and game has end conditions, this algorithm will terminate. And this is just some notes on the exact pseudocode. And you can read these some extra notes on that if you want from the slides. Right. Game tree size discussion. If we wanted to use minimax for tic-tac-toe, the average branching factor in tic-tac-toe is around 5. The size of the game tree is 5 to the power of 9, right? Or about 5 to the power of 9, because the game on average ends around 9 turns. I mean, it ends in exactly 9 turns, not on average. So the branching factor is on average 5, and the game exactly ends in 9 turns. So the game tree size is going to be 5 to the power of 9. This is how many game tree nodes there are in tic-tac-toe. This is not a lot. We can easily run with modern computers. So exact solution is quite reasonable. How about for chess? For chess, the average branching factor is around 35. The average depth of the game is around 100. So the average is that the game ends in 100 turns. That means using these averages, the game tree size is around 35 to the power of 100. That means 10 to the power of 154. So definitely I cannot generate the full game tree for chess. I can't use the minimax algorithm as is. For many games, I can't use minimax. But do you need to explore the whole game tree? Here's one idea we'll look at. Let's use shortcuts using alpha beta pruning. Um, And another idea we can try is we cut off the search at some depth limit and use heuristic functions to evaluate. Another idea is to cut off the search again at some depth, but this time we'll use simulations to estimate the heuristics or how good the states is. So let's talk about minimax with alpha beta pruning. This is the first speed up that we'd like to apply with minimax. So minimax can compute the optimal action, but we need to look at the full game tree. However, one thing we can do is prune large parts of the game tree that make no difference on the final outcome. That is, we can compute the optimal action without searching the game tree. How can we do this? What we're going to do is apply something called alpha beta pruning. The reason for the naming is you'll see now. The idea is that in my game tree, I have game tree nodes, right? What I'm going to do is each node in the game tree is going to keep track of 2 extra values. So I'm just going to add 2 extra values, alpha and beta, that I'm going to maintain in each game tree node. Okay. Alpha is a lower bound, right? So it's looking at a lower bound on the best utility value that max can achieve. Only max nodes can change this value. Okay. Beta is an upper bound on the best utility value that max can achieve, and only min nodes can change this value. So if I maintain, a lower bound on the best utility that max can achieve and an upper bound on the best utility that max can achieve in each game tree node, what this means is that at any game tree node, I know what is the bound on the best value that max can achieve. I'll know the bound because I'm maintaining alpha and beta. And this can help me reduce parts of the search space. How this is done, we'll see it right now using an example. So if I wanted to use minimax as is, it will search for this situation that you see here. It'll search the entire tree, right? It'll go down this path, and then this path, and then this path, and determines the utility here. Then it goes down this path, right? It has to search the full tree to determine the action. What about if I want to apply alpha beta to this tree with this simple tree? How will it look like? Here's what we'll do. With alpha beta, I'm just writing the definitions for you, just so you know. Okay. Remember, in each node that you see here in the game tree, as we explore the tree, we're going to maintain 2 extra variables, alpha and beta. Alpha is the lower bound on the utility that max can achieve. Beta is an upper bound. Another important thing is that only max nodes can change alpha, and only min nodes can change beta. Initially, when I generate the root node, the best value that max can achieve is unknown. I don't know the lower bound and upper bound because I haven't even searched anything in the tree. So initially, if I don't know what the upper bound and lower bound, I'm just going to say that the estimate of the utility, or what I know about the utility, is going to be bounded between minus infinity to infinity. When I search the tree using alpha beta, here's what we're going to do in terms of conditioning. If whenever my lower bound becomes larger or equal than my upper bound in a game tree node, I will cut off the search and backtrack to the parent. All right, this is the condition because this is the condition I'm using to know where I don't need to continue searching. And I'll talk about it through this example. If I am at a max node, anytime I encounter a new value from a child, I'm going to modify alpha to be the max between alpha, the current value for alpha, and the value I just returned from the child of the max node. If I'm at a min node and I just returned a value from a child, I'm going to modify beta to be the minimum between the current beta and the value I just returned from the child. So this is the things we're going to apply at each point in my game tree node. So let's start. This is my current situation. I'm going to go down this path, right? When I go down this path, I generated a new node. So far, I don't know any information about my lower bound and upper bounds. One important thing is that when you generate a child, the child will inherit the current alpha and beta from the parent. So currently, the current alpha and beta from this parent, when I go down this path, is going to be negative infinity plus infinity. Now here, I'm going to go down. Right? When you go down, let's say that this is a terminal state. And again, actually, when you go down, you do inherit the same alpha and beta from the parents. Right? But let's say that this was a terminal state and the terminal state was 3. Because this is a terminal state, the value 3 will be returned to the min node here. Now remember, when the value 3 is returned to the min node, we need to apply this update. So what is the minimum between plus infinity and 3? Well, it's going to be 3. So we modified beta after returning the value of 3. So in the game tree node, there's actually 3 values that are being maintained. The value of alpha, the value of beta, and the current best value from the child of this node. So there's 3 values being maintained. So far, I don't need to do any pruning because alpha is still less than beta. This is the condition I use for pruning. So what's left to do is search down this path. So let's say I check the remaining. So I check down this path and I check down this path. When I check down this path, I have returned a 12. Now, what is the minimum between the current beta and 12? The current beta is 3. The minimum between 3 and 12 is still 3. So no change to beta and no change to the current value because min is playing optimally. So he's going to select minimum utility. I go down this path. I return an 8. The minimum between 3 and 8 is 3. And beta also, the minimum between the current beta and 8 is still 3. So I check the remaining leaves and none change the best value or beta, right? So now I've exhausted this tree. You can see so far it's operating just like minimax. Now, after exhausting this part, I'm going to return the value at the node here to the parent. I'm not returning the alpha and beta. I'm returning the value at the node, which is 3, back to the parent. When I return the value back to the parent, remember, at a max node, you take your current alpha and you check what is the max between the current alpha and the value that you just got from the child. Well, the value I just got from the child is 3, and the current value of alpha is negative infinity. The max between both is going to be 3. And of course, one extra thing is the current value of this max node is 3. We're still not done because at this point, this condition is not satisfied. 3 is not greater than or equal to plus infinity, so I'm not going to prune anything. I'll go down this path or even this path. The ordering, depends on how you write it in terms of the code. But let's say we went down this path. The child will inherit the current alpha and beta. So at this node, this is the alpha and beta. After going down this path, let's say I found that the utility is 2. that utility will be returned. And my beta has now been modified. So the beta was 2, was plus infinity. A value of 2 was returned. What is the min between plus infinity and 2? It will be 2. And here's where an interesting thing comes up. What's the interesting thing is that the lower bound is 3, but the upper bound is 2. So the condition for pruning has been achieved, meaning that we have 3 here. Is 3 greater than or equal to 2? Yes, it is. So I can stop the search here and return whatever the current value of the node is to the parent. The reason you can stop the search is because of the following scenario. Why does alpha beta work, and why is it okay to stop the search? Well, the reason you can stop the search is as followed. When I searched this part of the tree and I returned the value 3, at this point in the search, Max knows that the best value it can achieve so far in terms of utility is 3. This area of the search tree could actually give me better utility, so I'll need to explore it. So when I explore this part of the search tree, down this path, I'm going to pass the current best bounds that I have at this node to the child. So this child inherits that bound. So why do we want to inherit the bound? Is because at this point in the tree, in the search, Max knows, because remember, Max is running this code. He knows that the current utility that min will return is 2 at this path in the search tree. He knows that min will either return a 2 back to him, or he will return lower than a 2, because um, because the utility is 2. Of course, if he returns a 2 or anything that's lower than a 2, Max will not go down this path. He will just go down this path. So the current best utility that he found down this path is better than a 2 or anything that's lower than a 2. And the reason is Max knows at this level that either min will return a 2 back to him, or after exploring the rest of the branches, he will return something that is less than a 2. All right, because if this was a 12, Max will not select this action, right? He will prefer the lower utility, which is 2. If this was a 1, right, he will return this action, so this will be a 1. But this doesn't matter, because a 2 or a 1, if a 2 was returned here, Max will not select this path here. He will select this path because it's a 3. If it was a 1 that was returned, Max will still not select this action. He will still select the left path, right? So the idea is that with these bounds, it allows us to find ways where, okay, at this point in the search, I know that I'm going to return a 2. So we know that min will return a 2 to the parent, or something less than a 2. But it doesn't matter if he returns a 2 or something less, because so far in my search, I know that the left path is going to give me better utility, right? So there's no point of searching down this entire subtree. Okay, so at this point in the tree, this is pruned, and then 2 is returned to the parent. And remember, at this point, when you return a value of 2, you check is the max between the current value of the node 3 and 2 is going to be 3, and the max between the current alpha and 2 is going to be 3, right? And then finally, I still need to check down this path because the condition for pruning has not been achieved. And when I check down this path, right, you inherit the parents alpha and beta, and then return a 14. When a 14 is returned, the minimum between beta and 14 is going to be 14, right? So 14, and the best value is 14. And then 5 is returned from this path. The minimum between 14 and 5 is going to be, 14 and 5 is going to be 5. And also the value of the node was 14, now it's 5. And then 2 is returned. The value now became 5, and beta now became 5, right? So at this point, when we had beta, so this point in the tree, when beta became 14, the condition for pruning has not been achieved. So we don't prune. At this point, when beta became 5, still the condition for pruning has not been achieved. At this point, when beta became 2, the condition for pruning has been achieved, right? 3 is bigger than 2, but what's the point? You already finished the branching factor. If we actually went down this path first and 2 was returned, then beta would have become a 2, and I could have pruned this part of the search tree. So the order in which the paths are searched can affect alpha beta. So this is just a small tree. I just wanted to showcase how alpha beta works. Definitely expect questions on, given a tree, you need to apply alpha beta to determine which parts of the tree have been pruned, and you need to maintain, right? This is, I would say, a nice guideline to really understand and memorize, because in each tree, in each node, you need to maintain alpha and beta, and these will be your update rules. So again, at this point in the tree, the entire tree has been searched, and Max will know that the action he should take is go to the left here. This is the code for alpha beta. Actually, not a lot has changed from minimax. The only thing that's changed is the following. You can see that this is the start of the search. This is the root node call. But one thing that we added is that at the max nodes, we have added two extra variables, which is alpha and beta. You can see here also at the min node, alpha and beta. At the root node, right, the alpha and beta is negative infinity plus infinity. As I search the actions or the branches from a given max node or a min node, you can see here that we're calling min nodes for them. Like if this is a max node, we're calling the min node, but we pass the parents alpha and beta. Similarly for a min node here, like this is the min node, when we call the child max node, we pass the alpha and beta. So it inherits the current alpha and beta. And as I loop on the children, you can see here I'm updating alpha and I'm updating beta here. And the condition that you see here is the condition for pruning, right? This is similar to just saying if alpha becomes greater than or equal to beta, then just stop the search and return. You can see that this is within the loop for the children. And you can see this is similar to just saying the same condition, is alpha greater than or equal to beta. So it's a very simple modification, and this is alpha and beta modification of minimax. But in terms of efficiency and properties, despite pruning parts of the game tree, it can still guarantee optimal decision. With good child ordering, because I just showed you an example that, for this left branch here, when we were exploring it, because of the order in which we explored the children, we really didn't get any savings. However, if we actually went down this path first and a 2 was returned, then beta would have been modified to 2. And the condition here for pruning would have been done, and I would have been able to prune this part of the search tree. So the ordering can affect the efficiency because it can affect how much is pruned. And in terms of space complexity, since we are still using the tree-like algorithm, it can be OBD or OD according to the implementation. With this implementation, it's going to be OD. In the worst case time complexity, the branch explorations are ordered so that no pruning takes place. So in the worst case, actually, your ordering could be this kind of bad ordering, right? Where no pruning takes place. We could have also had bad ordering for these nodes here, right? For these nodes, we could have explored this, then this, and the condition for pruning may have not been achieved, and then this, right? So you could have had bad ordering. So in the worst case with bad ordering, it can just become the behavior of complete minimax. The best case time complexity, if you can have so-called perfect ordering for a particular game tree, and that would prune up to half of the search tree. So OB to the power of D divided by 2. With random ordering, right, meaning that you just explore children in a random order, it's been found that in practice for toy games or research type of games, it's been found that you can get close to like 3D over 4, right? So it's kind of what I want to say is it's kind of saying that the best case is you can get B to the power of D over 2. The worst case is you can reach B to the power of D, and kind of the average case is getting to about B, 0.75 to the power of 0.75 D. In practice, you can use simple heuristic based ordering schemes to get close to OB to the power of D. And that means you can use clever tricks for your particular game to calculate which child you should have. We won't really discuss this, but good to keep in mind. So even with perfect ordering, even if you are able to achieve perfect ordering and get this very, very nice reduction, it is still too large for games like chess and Go. There's way too many states to explore, even with this reduction. So Alpha beta is good to keep in your arsenal. It's easy to implement with once minimax is implemented, but it can still be too much work that you need to do for some games. So we need more reductions in terms of speed. I recommend this site for getting practice. You can expect questions in the exam on you're given a game tree, and the goal is apply alpha beta to this game tree. So this is a nice, I would say, website to generate random trees and see your solution. Okay, let's say we want to speed up the search some more. What can we do with minimax and how to modify it? One idea you can do is apply a cutoff and apply heuristics at that level. So we mentioned that OBD can be too much for some games. What can we do to speed up the search? We can cut off the search at certain nodes in the game tree or a particular level. Let's say I'm going to cut off the search at level 2. When we cut off the search at level 2, this is most likely not a terminal state. And so we just need to use a heuristic function to evaluate how good that terminal state is. The cutoff condition can be anything. You can make it a depth limit, or it could be you look at the state and then see if the state satisfies certain conditions. For our case, we're just going to assume that we're using a depth limit just for learning purposes. So let's see how we can apply this to minimax. Very simply, this is the minimax algorithm, right? If we want to apply a cutoff at a particular depth, the issue is that most likely the state at a particular depth, let's say depth 2, is not going to be a terminal state. So when we reach, let's say, depth 2, how are we going to evaluate the utility of the non-terminal state? We are going to replace utility with a heuristic. We're just going to call it eval. This eval will take in the current state, which is most likely not terminal, and the player, and it's going to evaluate an estimate of the expected utility of state S for the player P. Like, how good is this state? And it's an estimate of it. So this is what our algorithm will look like. My heuristic minimax is going to maintain a depth variable if we're using depth limited minimax. It's still the same algorithm. We're still going to use a recursive method. At max nodes, we're going to just loop on the actions and take the max of the utility of the actions. At min nodes, we're going to take the min. And one thing you see here is that we are, when we're at a max node and we call a child min, we're going to call the h minimax with the resulting state, but we're going to pass, if this is depth d, we're just going to pass d plus 1 to maintain the depth. Then if we're at a node, right, in my tree where the cutoff test is achieved, right, maybe we reached a depth limit of 4, yani from the root node, we go down the tree and we reached, let's say, a depth limit of, let's say, 4, where the root node, let's say, depth is 0. If we reach a depth limit of 4, we just stop we stop going down the tree at this level, right? We cut off the search, and we just need a way to evaluate the state at level 4, right? So we're going to use our heuristic. So how do we design heuristics? Here's some function properties you would like. A heuristic value, it estimates how good the current game state configuration is for a player. We typically want to evaluate how good it is for the player P or how good it is for the opponent and subtract the opponent's score from the player's score. So for example, in chess, one heuristic you can use is what is the value of all the white pieces minus the value of all the black pieces. The heuristic function that you develop, the must-have properties for the the performance of the algorithm with the heuristic to do well. For terminal states, of course, you want your heuristic to just be the exact utilities for terminal states. For non-terminal states, the heuristic value should be between a win and a loss utility value for the game. Formally, right, your heuristic evaluation for a state, any state in your game, should be between the utility for a loss and the utility for a win, right? And it should that this condition or this property makes sense and is reason. I mean, it should happen for the heuristic that you develop. Other than these two requirements, what other properties are preferred? Definitely, it should not take too long to compute. So what you notice here is that every time we reach the cutoff condition for a state, we're going to have to calculate this. And this is a function that you implement in your code, and it takes the state and it will evaluate it and run the computation for that state. It looks at the state, looks at what properties the state has, and computes this. So you don't want your you know, for every time you reach the cutoff condition, you don't want the computation to take too long. The purpose of the heuristics is to speed up the search. Another thing is that it should correlate with the chances of winning. Otherwise, it would not be a helpful heuristic. Finally, for two non-terminal states, if you have two non-terminal states, state S and S dash, if the state S is more likely to lead to wins than the state S dash, then it should be that your heuristic evaluation of state S should give you a value that's better than the heuristic evaluation for S dash. Okay, so these are some properties of heuristics that you would like. How do we develop a heuristic? One idea is you want to compute features from a current game state. Then the heuristic is just a function of these features, right? So here's an example from chess. A chess state, here's one way we can compute some features from a current game state. One feature for the current game state could be the number of white pawns minus the number of black pawns. This tells me what is the pawn advantage of the white player, right? Pawn advantage. And you can assume that white is your max player, right? So this tells me how good this state is in terms of the pawn advantage for the max player versus the min player. Here's another feature. You can compute the number of white knights minus the number of black knights. This gives you the max advantage for the knights pieces, and it could be the white queens minus the black queens. And it can do this, for example, the bishops. You can do this for the towers and so on. And one way your heuristic could be defined is as follows. It could be a linear weighing of the features you just extracted from your state. It's, the amount of weight I want to give to the pawn advantage, the amount of weight I want to give to the knight advantage, and the amount of weight I want to give to the queen advantage. The linear weighing here is assuming that the features of a state are independent of each other. This is just a property of linear weighing. In some problems, it may be better to combine features non-linearly. So this will be a non-linear combination of the features. This would be a linear combination of the features. And which is better? Well, which is better? Should you use this or this? Again, as I mentioned many times in this course, if you have competing ways of applying to a particular problem, then the best way to determine which is best is to do experiments and see which is performing better. So if you say my cutoff depth is at depth, let's say 2, and I have 2 heuristics I want to try, I'll run random initializations of the game and try both heuristics and see which is giving me lower reduced search work with better decision-making capability. A question then arises, if we develop heuristics this way, we talked about weights here, right? How do you set these weights? Well, there's two ways you can do it. You can run computational experiments with various weights and compare the results. A better idea, which we won't really discuss for this game setting, is you can use machine learning. You can use experience from previous games, which is historical data, where the data is going to be game states and the outcome from those game states, so where they wins or where they losses, right? And using this as data, you can feed it to a machine learning problem to learn what is utility. You can learn a heuristic using machine learning algorithm, right? So this is kind of an advanced idea. We won't really discuss it. So in our course, we're just going to say, imagine if you develop the heuristic manually and you define, a set of features, you computed it. This is the H minimax algorithm. This is the minimax algorithm, and this is the H minimax, how you would convert this to H minimax. What you need to do is replace terminal with your cutoff and utility with the heuristic. That's pretty much it. And you also need to pass the depth here, right? So an extra argument would be the depth plus 1. That's it. That's the modification to minimax to make it H minimax. And of course, I want to mention that when you replace the utility with eval, you need to have this eval function somewhere coded that takes in a state and the player. You can also apply alpha beta with this heuristic minimax. How would you modify it? Well, again, you still need the cutoff condition. right? This doesn't change. However, here you would add alpha and beta as well as the depth, right? And one interesting thing is that now alpha and beta in this scenario is not operating on the utilities, it is actually operating on the heuristic. So what happens is that you will lose guarantees. So I'll talk about this with the properties of H minimax, but definitely you can use alpha beta with the heuristic in terms of can you do it? Technically, yes, you can write the code and do it. So let's just look at the application of H minimax with a toy problem. So let's say I want to develop a heuristic for tic-tac-toe. One interesting heuristic you can use here, a very simple heuristic, is given a current state of the game, let's say this particular state, I want to compute the advantage that Max has. And Max is the X player, Min is the O player. Well, the advantage we can develop with using a heuristic is the number of win lines available for Max, which is the X player, minus the number of win lines for the Min player. And by win lines, we mean how many ways from this current state can Max win. If you look at this state, the number of ways that Max can win from this state is he can win by putting X here and here. He can win by putting X here and here. So that's another win line. He can win by putting X here and here. So the number of win lines for X is 3. Oh, also all the other win lines, my bad. So you also need to account for this. So this is the total number of win lines that X has. So X has 6 possible win lines. So for this current state, the heuristic evaluation of this state, so H of S, is going to be the number of win lines for X, for Max, which is 6. And the number of win lines for O is 5, minus 5. Right? So the heuristic for this state is going to be plus 1. And this gives you the how good this state is. It is a 1 advantage for Max. How about this state? Again, X has 4 possible win lines, O has 6 possible win lines. It's a negative advantage. So if you had 2 game states here, and we are using this heuristic tells us that this state is a worse state than this state. Whether or not this is true, you can't know for sure. The heuristic, again, is just some heuristic that you developed. It may be a good or bad heuristic, but nonetheless, it gives you some ranking of the states. Here's another third state. It's still an advantage for X. How do we do this in practice? The way it's applied in practice, let's say I have the empty board initially. Max will, start the root node, Jamil, and then he'll look at available actions. And I'm not looking at all the 9 possible actions. I'm just, because the tree will be too large. I just want to show if he's just going to look at 3 actions. If he goes down this path, he's looking at the action where he applies an X here. And let's say we want to cut off the search at depth 2, right? So this is depth 0, depth 1, and this is depth 2. At this point in the search, this is the min node, right? And let's say he goes down this path. Now he's reached the cutoff depth. And at this point in the tree, in this state, he's going to apply his heuristic evaluation. And he found that this node has a utility estimate of 1. So 1 is now returned here, and the best estimate so far for min, this is a min node, is 1. Then goes down this path, it finds a 0. The best estimate for this is 0 at this point. Then here, then here, then here. And if you look at all these children of the min node here, if it's trying to play optimally, it will select the minimum utility estimate, which is -1. So min at this node wants to go down this path. Right? Searching down this path, we again apply H minimax. You can look at all these heuristics here. It'll be -2. So min wants to go down this path. And if you look at down this path, min wants to go down this path here. And so after searching the full tree, or the tree up to depth 2 using H minimax, Max is going to select the one that maximizes utility down this path. So let's say Max goes down this path. In the real world, he puts an X here. Then min takes an action. Let's say that in the real world, from this current state in the real world, min will select O and select the middle top O here. So min selects O here. When min selects O here, it'll be Max's move. Max will look at the game world and then will start his root node. This is the root node for Max. And then he'll do H minimax again, right? And you can see he'll cut off the depth, the search at depth 2. right? And then applying H minimax, he knows that he should go down this path here. He applies the action, and then so on. This is the current state in the real world. O will take a turn, and let's say that, O takes some action. This is the current situation. Again, H minimax will be applied up to depth 2. So the idea is that H minimax is a way for you to cut off the search early in games where you don't have a lot of time, or the game tree is just too large for you to realize it fully. So, some properties of heuristic minimax. Is heuristic minimax optimal? No. There can be uncertainty or error in estimating the utility or your heuristic. Is heuristic alpha beta? No. There can be also uncertainty in the heuristic, and I would say that heuristic alpha beta is less optimal than heuristic minimax. They're both not optimal, but with alpha beta, you're also making you're making bounds on a heuristic, so it can be more, I would say, a less better strategy than heuristic minimax. But nonetheless, you can still apply it. Remember, the whole point of applying heuristic minimax is to speed up the search. And if you wanted to speed up heuristic minimax even further, you can apply heuristic alpha beta. What if the game is timed? How do we set the cutoff depth? Like I said, you can use depth limited. A better idea is you can use iterative deepening. Okay. And by that idea, you can say, okay, I have a timer. That timer is going to continue timing down. From the start of the timer, I'm going to apply H minimax up to depth 1 and save the solution that is returned by here. I'll save it here. It says action 1 at the root. And then if I still have more time, reapply the search again up to depth 2. And then let's say it says return action 2. So now I know that this search here is more exhaustive, so I'm going to return action 2. Let's say the time still hasn't run out. Run up to depth 3. And let's say it tells you return action 3, and so on, until the timer runs out to return the deepest completed search. The cutoff condition can also be restricted to specific states to improve the quality of a search. So you don't have to use a cutoff depth condition. You can use a state condition. For those interested, this is kind of an advanced topic and related to games like chess. You can look at something you use quiescent search. We won't go into the details. We just need, this is just for your information. More techniques you can find from the book for those interested. And that's just the discussion. In terms of time complexity of alpha beta with heuristics and a cutoff at depth D, with perfect ordering, you can achieve, again, OB to the power of D over 2. Using some of these techniques, how fast can we make a move in chess? So let's see. Chess has a branching factor of an average of 35. Using minimax with heuristic plus cutoff test with something called quiescent search plus a machine that can evaluate 1 million nodes per second with a time limit of 1 minute, we can search up to depth 5. This is not, remember, the average depth in chess is about 100. So this is not a lot of depth with a 1 minute time limit. This bot or this heuristic minimax can be beat by an average human chess player. If we use alpha beta with the heuristics, plus a cutoff test with quiescent, plus a machine that can evaluate 1 million nodes per second, plus a large lookup table where we cache the best moves for some of the states, with a time limit of 1, we can search up to depth 14 in the game tree. This achieves expert level play. Stockfish, which is a popular bot, it uses alpha beta with fine-tuned heuristics using machine learning, plus a cutoff test with quiescent, plus a huge lookup table, plus a database of opening moves, plus a huge number of compute resources. It can use up to 1024 CPU threads, transposition table. This is something related to chess. And using all of this power, it can finally reach a depth of 30. This is grand level play. Again, the average depth can reach up to 100. So, up to depth 30, this is what Stockfish uses. So using these techniques, you can implement a popular or close to popular. Stockfish uses some extra things that we didn't discuss here, but you can definitely come up with a powerful chess bot, at least up to this level. AlphaZero also used some of these techniques as well.